Hey, I'd like to talk to you today about Chapter 1 in the book. As you can see down here in the bottom corner, this starts on page 1 of your red yellow book, Mr. Beiser's book. These notes, these slides that you're looking at are also in the lab manual. So if you want to open up your lab manual, you can kind of follow along, maybe make some notes as we go. However you want to do it's fine, but they're there if you want them. Okay. In Chapter 1, we're talking about a math review. We are looking first at some ways to use numbers. Now, you should know that in science we use some very large numbers and some very, very small numbers. The first one here is a classic example of this, 300 million. We use this number all the time. If you put units on it, if you tell people what you're measuring in, the appropriate units here would be meters per second. And 300 million meters per second is the speed that light travels. So that's a pretty big number. A meter's, the distance from the floor to the doorknob, or a little bit longer than a yard. So that's pretty fast. Works out to about 186,000 miles per second. But this 300 million here, it's got all those zeros, and it's these zeros that we're kind of interested in here. They're really just placeholders, right? They're really just shoving 3 far enough to the left to make this into 300 million. So what we can do here is say that's really 3 times 100 million, and 100 million is just 10 times 10 times 10 times 10, 8 times. So right here, another way to write 300 million is to put 3 times 10 to the 8. It's easier, more concise. It's a lot easier to put in on your calculator. If you don't have a calculator, then you just multiply by 3 and then move the decimal place 8 times. A lot of advantages to doing this, working with these large numbers, and this certainly is not the largest of them. When we get to the astronomy part and we look at some of the numbers involved with space, how far things are apart, and the size of things, the numbers are just so crazy big that you almost have to go to some kind of system like this. You'd be writing zeros all day long if you didn't. So it's a handy thing. Now, there is a little shorthand way to do this. You see, it's really this 3 that we want to keep, right? Again, the zeros are just placeholders. So if I want to put the decimal place right after this 3, how many times would I have to move it? Well, it's here now, so that would be 1, 2, 3, 4, 5, 6, 7, 8. And see, right there's that 8. So all you really got to do is move your decimal place to after the first digit, count how many times you moved it, and then put that as the exponent there. Here's a second example. This one uses a small number, 0.0000052. So this by no means is the smallest number we use in science, but just as an example, we could do this one. Here it's the 5.2 that we really want to keep up with. So go ahead and write that down, 5.2. In order to get the decimal place after the first digit like we did before, it's here now. I want to move it to there, so that would be 1, 2, 3, 4, 5, 6 places. And so I've got the 5.2 times 10 to the 6. Notice I moved the decimal place the other way. I moved it to the right this time, whereas up here I moved it to the left. So that -6 there says move the decimal place 6 times, but move it to the right. And if you've had a little bit of math, you know that a negative exponent inverts the whole thing. It flips it upside down. So we're really dividing by a million there. Okay? But it works for big numbers, works for small numbers. Lots of examples in the book, and I'll be happy to do some in class or wherever you like. But after, my office or whatever. But it's a nice way to work with numbers. We'll do a little bit of it, so you need to kind of know what it is. Practice some of those. The second thing here is called unit conversions. And every time we make a measurement, and that's pretty much all we do in science. We're trying to measure things and see what we can learn, see what we can put down, quantify. So there's lots of different ways to measure. I could measure a distance of 30 feet, and maybe I need to know how many yards that is. So this is a real simple little way to go through and get the units to convert to what we want. You do have to know a conversion factor. Right here, 3 feet is the same thing as 1 yard. And so as soon as you know that conversion factor, you write it down, then all we need to do is take the number they give you, 30 feet, put in a little set of parentheses here, and on the bottom, you're going to pick up the part of the conversion factor that has the same unit as your number. So see how this was in feet? It's on top, right? There's really a divided by 1 here. So you're writing it like a fraction, it would be 30 over 1. The top part, the feet there, I need to get that same unit on the bottom. So pick up this part that says 3 feet, put that on the bottom. The other part has to go on the top, right? There's nowhere else for it to go. Feet on top, feet on the bottom, cancel. And here, when I do this, I'm really saying 30 times 1 divided by 3. Of course, the times 1 doesn't do anything, so we just kind of ignore the ones. But 30 divided by 3 would be 10 yards. Now, that's a pretty easy problem, and you could have done that in your head. But the point is that you can use this technique to do any kind of conversion that you need to do. All you got to do is know the conversion factor, watch the units. If you want to cancel feet, put that same unit opposite. If this one's on the top, put the other one on the bottom, like that. And then whatever number is here, you multiply by. Whatever number here is, you divide by. Okay. Here's going the other way. If I had 3.72 yards, needed to turn that into feet, I'd take the 3.72 yards, and I set up my conversion ratio here, like this. This time I'm in yards, so I need to pick up the yard part. Yards on top, yards on the bottom. The 3 feet has to go on the top. Notice that the units cancel out. I will now be in feet, so that's good. Here's my 3.72. The 3 is on top. If it's on the top, you multiply. Back here, it was on the bottom, so we divided, right? Top, multiply, bottom, divide. And I do that, and it's 11.16. So it's a real nice, easy way to convert. All it's really doing is telling you whether to multiply or divide by 3, but this way you can see it happening. You can know why you're multiplying by 3 or dividing by 3. It's because the unit needs to cancel out. Sometimes these get a little bit bigger and more involved. Right here, for example, I got 3.1 miles. I'd like to take that to meters. Well, I'm looking at my conversion factors up here, and I don't have one from miles to meters. I've got right here's feet to miles, and this one's meters to feet. So what I'm going to have to do is, since I'm starting out in miles, I got to do something about miles, right? Right there's miles. So put this one's on the top, put the other one on the bottom. That forces the other part of this conversion factor into the top, 5280, and I put it down right there. Looking at the units, miles on top cancels miles on the bottom. That puts me into feet. I don't want to be in feet, I want to be in meters. So now I come over to the other conversion factor. I'm in feet, put the feet on the bottom, but that leaves meters on the top. My feet cancel out, and now you see I'm in meters. The units tell me where to put the pieces, and then I go through and do whatever it says. Here's a 3.1, 5280 is on the top. If it's on the top, I multiply. So right there, 3.1 times 5280, and 3.28 is on the bottom, so I divide. There's my answer right there. This one, we're going the other way, so everything's just going to be turned upside down, right? Take the 50,000 meters. I need meters on the bottom. Right there's meters, and I can go to feet. So I stack that up, meters cancel, I'm in feet. Now I want to go from feet to miles. So here's my feet. I put that on the bottom, my feet cancel out, my miles go up top. And looking at this, 50,000 times 3.28 divided by 5280, 31.1 miles. Okay, these take a little bit of practice, and some of them are trickier than others, but unit conversion is an important thing. So do some of those in the book. There are some homework problems for Chapter 1 that are a lot of them are unit conversion problems, so give those a try. Now, there were some people that got tired of doing unit conversion, so they came along and they said, we need a better system. And that better system is called the metric system. And what's so beautiful about the metric system is that it's all based on powers of 10. You notice here going across that there's one unit, the meter. So we're talking about length here. A meter, again, is roughly the distance from the floor up to the doorknob, something like that. So it's not a great distance. But if I need to talk about bigger distances, then I could talk about 10 meters at a time, or 100 meters at a time, or 1,000 meters at a time. It's only one unit, the meter, but I put these prefixes on them. Deca means 10, hecto means 100, kilo means 1,000. A kilometer, abbreviated km, would be 1,000 meters. And so you see the power of 10 there? What happens when we multiply by 10? We just move the decimal place, right? We can go the other way. Right here, decimeter, dm, is a tenth of a meter. That's 0.1 meter. Right here, centimeter, 0.01 meter. Millimeter, mm, 0.001 meter. So, you've got your tenths of a meter, hundredths of a meter, thousandths of a meter going the other way. This arrow goes a long way both directions, right? You go another 3 spaces here, you got megameters, and another 3 spaces would be gigameters, and another 3 spaces would be terameters. But let's just worry about this little piece right here, and we'll do some examples here. If I started with 3.72 decameters, and I wanted to go to centimeters, you can see the little red arrow here. I'm starting with decameters, so that's right here. I want to go to centimeters, that's over here. That's 1, 2, 3 hops to the right. So I take my decimal place right here and the number they give me, and I move it 1, 2, 3 places to the right. Now there's a hole right there, so I fill that in with a 0. But that's all I have to do to convert in the metric system. Just slide the decimal place. It's a really nice system once you get used to it. Here, for example, is 1,200 centimeters going to meters. Well, centimeters would be here. Meters is there, right? So that's 1, 2 steps to the left. So I take my decimal place, which is here, and I go 1, 2 steps to the left. And these things work just like a champ. Right here, 1655 decimeters, right? Decimeters are there. I want to go to kilometers, which are way over here. That's 1, 2, 3, 4 steps to the left. Here's my decimal place. 1, 2, 3, 4 steps to the left. And you see that's where it is right there. Okay, so this metric arrow is really nice to kind of learn and everything. You do have to get it in the right order, and there's a little ditty down there in red that kind of helps you get it in the right order. King Henry died. You can see that's the K, the H, the D. Don't call me. Some people use don't or drinking chocolate milk. There's all kind of stuff you can do to remember this. But you set up that little arrow and zip, zip, zip. You just move it wherever it needs to be. Play with some of those. I wanted to mention real quick here a concept called a vector. A vector is a mathematical idea that is used to express any quantity, any measurement that has both length and distance. Or another way of saying that is magnitude and distance. If it has a number associated with it and it points a certain direction, we can use a vector to represent that. Right here in the little picture, you see that there's a little guy standing there, and he's going to walk a certain distance this way. Let's say it's 30 steps. And then he turns and he walks 40 steps this distance, and then he turns and walks 60 steps this distance, right? You can see that the 30, the 40, and the 60, those are the numbers that are associated with the magnitudes, the lengths, whatever you want to call it, the number. And there's also clearly a direction, and that direction changes over the course of that thing. So if I use a vector, here's vector A, vector B, vector C to represent the 3 legs of this trip. Then I can write a vector equation, A plus B plus C equals R, the result. The result is the guy started here and walked to right there. And you can either follow the red path or you could follow the dotted blue path. You end up at the same point in space. So vectors can be added. It takes a little bit more math than we're going to have to do that. It takes trigonometry and algebra. But so we won't do that. But I'd like you to know what vectors are. Here's another example of a vector, force. Right? Here's a box, and somebody comes along and pushes 40 pounds to the right, but somebody else is pushing 20 pounds to the left. Opposite directions there. This guy's going to cancel out some of that guy's effort, right? And so if we set up a little coordinate system here, plus to the right, minus that way, then I could say that the 40 is in the positive direction, 20 is in the negative direction, write a little thing like that. The result of this vector equation is that the box feels a net force of 20 pounds to the right. If they both push in the same direction down here, if the first guy is pushing 40 to the right, second guy pushes 20 to the right, now they're both pushing in the same direction, both in the positive direction, if you will. So those forces add together. There's a net force of 60 pounds on the box. And of course, we could go to 2 dimensions or 3 dimensions or how many ever you want. But again, you got to know trigonometry to kind of take care of the mathematics of that. And we won't worry about that. The only thing I might ask you to do with vectors is right triangle, like you see here. And in this example, we're moving some distance, let's say south, and then we're turning to the east and traveling some other distance. We would like to know how far away from home we ended up. Okay, so if I walk 200 miles south, if I turn and go 60 miles east, then this is a right triangle. So what I can do is use the Pythagorean theorem. This thing right here, r, the length, the distance from there to there, the result is equal to the square root of the first side squared plus the second side squared. And so I put in my numbers. A was 200 coming down that way, and I have to square it, multiply it by itself. Right here, 60 was the second side, square that. If you'll just put this into your calculator, just like it shows, depending on what calculator you have, if you type square root, it'll automatically put in this parenthesis for you to hold all this together. Take the square root of it at once. 200, hit your squared button, plus 60 squared, and then hit equals. It'll give you the right answer. Now, some calculators, you have to have the number and then tell it to do the square root. So if this didn't work out for you, then try it this way. Put in your 200, square that, plus 60 squared equals, you get a single number, then you can take a square root. But if you have a graphing calculator, TI 83, 84, 89, this is what you want to do right there. Just put it in just like it looks right there. Well, good. That's the little bit of math review that we need for this. There's not a whole lot of math in what we do. These first 2 tests will have a little bit, but it will all be, here's a formula, put the numbers into it. At least on the test, I won't ask you to algebraically manipulate, move terms around and all that stuff. There might be a homework problem or 2 that's a step up from what we do on the test, but there's no real math prerequisite for this, so I can't ask you to do a whole lot. All right, math is a wonderful thing. It's how we measure and determine the rules of science. We will see a little bit of it here, but don't worry about it. We won't have to wade off too deep. Thank you much. Have a good day.